there is a drop in torque, there is a drop in power. Power, which was 45 bhp, now reduced to 41, and the torque was about 39 Newton meter. Now that is dropped to 30. The Duke 350, however, only generates 33.5 Newton meters of torque, and this is also coming at slightly higher RPM. Peak RPM actually drops. But one thing that KTM has not done is they've kept the red line RPM as the same. This could have actually increased the top speed as well, and ability to rev this engine will be much better. In terms of the work involved and in terms of the overall effort involved, this is the least amount of things that they could have done to make this happen. Now, one other thing that everybody is telling you on the internet is the 350cc engine has lower vibration compared to the 390. Why is it lower? The answer to that is there is a certain velocity with which the piston can travel, beyond which the wear on the engine will go up. The engine will start to wear out faster. The 350 should have a better engine life compared to the 390. The biggest drop will always come from first gear to second gear. This is something that is evident everywhere. That's why when you shift from first to second, you will either hear a hard thud, or in some cases, it feels like a little more jerky. KTM took the Adventure 390 and reduced the stroke to reduce the overall engine size by 50cc. They did this by reducing the stroke, but why didn't they change the bore? Why is it that we see a reduction in the torque output, but we also see a reduction in the vibrations in the 350cc? So today we will break down the Adventure 390 in a way where we give you engineering justifications to show you why the bike feels the way it feels. Welcome to Hennis Garage, and this is Hennis Breakdown. Now, this is a video format that we tried out last time, where we did break down the Royal Enfield Himalayan 4. Today, we will break down the KTM Adventure 390. Now, let's get on to it. KTM Adventure 390 has a drop in 50cc, and the price drop is about 60,000 rupees. What we see is, according to our review as well, there is a drop in torque, there is a drop in power, and there are a couple of changes that has happened. We are seeing power, which was 45 bhp, now reduced to 41, and the torque was about 39 Newton meter. Now that has dropped to 33. The part of the engine that has changed to make this happen is the stroke. What is the stroke? The stroke is basically this movement. Now this has changed, and everything else has more or less remained the same. Now let's look at closely on how the stroke has changed and what has happened. Now this is the Duke 390, and this over here is the Duke 350. Now if you look at the stroke on the Duke 390, it was 64 mm, which means it traveled this length. Now this length has reduced by about 8 mm, and this results in a stroke of 56.15 cc. Now this is how the 50cc drop has happened. So the way the volume is calculated is basically pi into d square, and you multiply this with the stroke length. Now the moment the stroke length is reduced, the volume, which is the cc, is also reduced. One question that might come up during this process is, why did KTM just change the stroke? They could have done something with the bore as well, right? There is a reason to it. In terms of the engineering effort required to drop the cc, the moment they touch the bore, they have to change a lot more things. For example, here, let's say this is the cylinder head. Below the cylinder head, you have the combustion chamber. Now, this combustion chamber length is actually restricted by the stroke. So this length is actually dependent on the stroke of the engine. And what is happening now is, because they're only changing the stroke, all they have to do is reduce the length of this. Now below this you have your crankcase and other things that come up. So without changing any of this or this, KTM has smartly touched and reduced a very small part of the engine, and they've reduced the overall cc of the engine from 398 to 340. In terms of the work involved and in terms of the overall effort involved, this is the least amount of things that they could have done to make this happen. The moment stroke goes down, whenever you drop the stroke, what happens is, let's say this is the crankcase and you have your crankshaft here. This is the connecting rod. So every time the engine moves up, the piston moves up and down, the crankshaft will create a rotation like this. Now, from the center, let's say this is the crankshaft center, I'm talking about this here. Let's say this engine had a certain stroke length. For that given stroke length, let's say this was the radius of the crank. The torque that is generated is dependent on the force that is applied here. We multiply that with the radius of the crank. So this is the origin of torque. The moment we reduce the stroke length, in the previous case, let's say this was the overall radius. Now with the reduced stroke length, this will be the new radius. So what has happened is the radius was no longer this, it is just this. Because of this, even though the force could still be the same, the radius has dropped, because of which the torque would have dropped. Now, if you look at the specification, the 390 has about 39 Newton meter of torque at 6,500 RPM. The Duke 350, however, only generates 33.5 Newton meters of torque, and this is also coming at slightly higher RPM. Now, as we go through this video, you will understand why there is a change in RPM, where the peak torque and peak power are coming in. We'll get to that. One thing to notice, although the Duke 390 and the Adventure 390 have a similar torque output, it is the same torque output, what we actually see is, because of the higher CG height of the Adventure, the perceived torque feels more. We'll talk about this more towards the handling section of this video. Now let's look at the peak power. Now how is power estimated? The way we estimate power is, now N is the RPM, this is a constant, T is the torque output, and 60 because you are converting RPM to RPS, revolution per minute to revolutions per second. Now what we have seen is, let's look at the RPM and the torque. We saw that between the 390 and the 350, the torque output on the 390 is high and this is low. So even if both of these engines are generating the peak power at similar RPMs, even though it is 100 RPM higher, because the torque is lower, the overall power output is much lower than what you would see on the 390. There are a couple of more interesting aspects to this engine. Let's go through those. Now, one thing is, every time there is one revolution, every time there is one circle of the crank, the piston moves by a distance of 2 times the stroke length, which means if the stroke length is 64 mm, it is 128 mm of travel per revolution. In the case of the Duke 350, it is 112. So what this means is, now imagine there is a person who has to run from point A to point B. Now this person starts from here, runs and comes back. Now in case of the 390 engine, 390cc engine, this distance was about 128 mm. Let's consider 128 meters. For example, somebody has to run from A to B and back. Now that total travel was about 128 mm. In a different case, the same person has to travel slightly less. Now, since the stroke length is reduced, it is equivalent of reducing this distance. And this is a new point C. Now, this new point C results in a lower distance of about 112.3. This person will be able to do more of these laps, which means they're able to do more revolutions. And in this case, the revolutions, the peak RPM actually drops. But one thing that KTM has not done is, they've kept the red line RPM as the same. Let's say it is around 9,500 RPM. This red line RPM is still the same. There is potential, however, in the second case, where they can increase the RPM from the current red line to later. This could have actually increased the top speed as well, and the overall ability to rev this engine will be much better. Now, this brings us to this point, which is the mean piston speed. Let us understand what mean piston speed is. First, we'll go to this and then we'll come back to that. So there are 4 strokes in an engine. One is the intake stroke, where the fuel and the air comes in. Next is the compression stroke, where the fuel and the air is compressed. Next is the power stroke, where the compressed air and fuel is burnt, which pushes the piston down. And the final stroke is the exhaust stroke. This is where the exhaust gases actually flow out. Let's consider this as 0 degree. Now in the intake stroke, the engine goes from 0 degrees to 90 degrees. Sorry, 180 degrees. So this is intake stroke. In the next stroke, the piston travels or the conrod travels and it covers the next circle, next half of the circle. This is the compression stroke where we went from 180 to 360, not 270, 360. In the next cycle, we go again from 360 to 540. Now this is the power stroke. And in the end, we have the exhaust stroke, which again goes from 540 to 720. Now that is what is listed here in the x-axis. You see from 0 to 180 is the intake stroke. From 180 to 360 is the compression stroke. From 360 to 540 is the power stroke. And the exhaust stroke is from 540 to 720. If this is clear, let's look at what points the speed of the piston is the highest. Now, whenever a piston moves, right? So let's say it is here. The piston will accelerate when it moves down and then decelerate in the end, which means the speed picks up, then drops. That is what is listed here. As the piston travels this way, the speed increases at 90 degrees, then drops again. While it is compressing, it increases speed again till 270, drops again. The same cycle repeats. Now we know that the piston speed is the highest at the center of the cylinder and it is near zero at the ends because it is changing direction. There is some things that we'll have to note. There is a physical limit to which the pistons are actually regulated. There is a certain velocity with which the piston can travel, beyond which the wear on the engine will go up. The engine will start to wear out faster. That is why you will see that people say if you rev the engine too much, it will wear out faster, you will have problems. In racing, we generally tend to rev the engine a lot more. Because of that, the life of the engine is also lower. Now, there is one rule of thumb where the wear threshold is actually related to the piston speed. That mean piston velocity is around 20 meter per second. Now, what is mean piston velocity? Basically, if you take the average of all velocities in this curve, now that is mean piston speed. Now over here, what we have is for different RPMs, we have what is the corresponding piston speed. Whatever is the dotted lines, this is a 350 and this is a 390. What you see is for the same RPM, now this is around 4000 RPM. For the same RPM, 4000 RPM, you see that the mean piston speed of the 390 is about 10 meter per second, whereas the 350 only accelerates to about 6 meters per second. Because of this, what you can also expect is the 350 should have a better engine life compared to the 390. Why am I drawing this line here? This is to show that even though there are times where the piston speed will reach about 20 meters per second, the average velocities will still be lower. It will still be somewhere around here. Now that is represented over here at a maximum speed of 9000 RPM. Mean piston speed in the case of the 390 is around 19.2, whereas it is 16.8 in the case of the 350cc. Now, one other thing that everybody is telling you on the internet is the 350cc engine has lower vibration compared to the 390. Now, why is it lower? The answer to that is somewhere here. I previously told you about the radius of the crank, where in the 390, let's say this is R here. In the 350, this is reduced to a smaller circle. Let's say this is R dash. The primary vibrations that is generated by the engine is taken care of by something called a counterbalancing shaft. What happens there is you have your crankshaft like this. Every time, let's look at the side view also. Every time the piston pushes down on this is rotating like this. Every time the piston pushes down on the crankshaft with a certain distance, it creates a certain force. If this is the crankshaft, the piston is actually pushing it down. The conrod is pushing it down. It rotates. Now, while this is rotating, there is a certain change in force. Now, that change in force is actually balanced by something called a counterbalancing shaft, where you have weights added to this crankshaft in a way where the overall dynamic balancing is taken care of. If this is taken care of, then why are there vibrations? This is where the secondary vibrations come into play. Now, the secondary vibrations are a function of your crank radius divided by the length of the connecting rod. Now, if the length of the connecting rod is this L and the crank radius is this much, you see these weights, right? These are actually counterbalancing weights. So the length of the connecting rod, con rod, is L and the radius is R. In the 350's case, it is R dash. In the 390's case, it is R. Let's say the lengths are still the same. Now let's compare R by L versus R dash by L. Assuming that the connecting rod lengths are still the same, what happens is, because the radius of the crank has reduced, the vibrations that come because of this, the secondary vibrations that come out because of this, also reduce. Now, let's compare how much is the reduction across different RPMs. At 4000 RPM, you'll see that there is hardly any difference. Now, at 6000 RPM, there is some difference. At 8000 RPM, the difference is clear. And if the engine revs to 10,000 RPM, there is some difference. Now, this perceived difference can vary anywhere between 5% to 15%. Next, we will move on to what happens with the drivetrain. Now, if you look at the transmission, the first thing and the most amazing thing on this bike is the Quickshifter. In my opinion, it is one of the best Quickshifters that you can experience in this price range, or up to 5 lakhs or in that category. Now, let's understand a bit about the Quickshifter and then we'll come to gear ratios. Let's move to the Quickshifter. Let me explain how a Quickshifter works. Whenever you're riding, whenever you're revving the engine, let's say you reach around 7000 RPM, let's say you are in first gear here. Now you want to upshift. So the moment you upshift, you go to second gear and the RPM drops to, let's say, 5000 RPM. Taking an example. How do you change gear? Step 1, you pull the clutch. Step 2, you upshift. Now, step 3, you dump the clutch. Now, this is what the rider does. Quickshifter does this. And why do you need the clutch to begin with? The clutch is required because, let's say at 7000 RPM or 8000 RPM, you are at a certain, now that speed might correspond to, let's say 55 kph. Let's say this is 55 kph. What we'll have to notice, at the same speed, if you try to change gear without the clutch, what does the clutch do? The clutch disconnects the engine from the road. Now the road speed or the tire speed is around 55 kph. But the engine is at different speeds. The engine right now has to suddenly come down from 8000 RPM to around 5500 RPM. To facilitate this, clutch have always been there. Now let's say somebody has to not use the clutch. That is what a Quickshifter actually does, no? You don't have to use the clutch, you directly upshift and then you keep going on. You can hold the throttle and keep upshifting. How does that work? Let's use this piston as an example for now. Now, this piston is actually going to and fro at 8000 RPM. What the Quickshifter does is, when you're upshifting, it cuts the ignition for a very small fraction of seconds. Let's say, depending on the RPM of the bike and depending on which gear you're in, the milliseconds to which the engine is cut off can vary. So let's say the engine cuts off to 200 milliseconds. 200 milliseconds is about 0.2 seconds. In this time, what happens is, your engine speed will match the road speed. This is as good as you're going at a certain speed, then you kill the engine. The moment you kill the engine, what happens is your bike starts moving with the engine being cut off. Now, the same thing is happening here. The engine is cut off for a very small fraction of a second. At this instant, the road speed and the engine speed matches. This entire exercise, let's say, would have taken you around 0.3 to 0.5 seconds on a good shift. By cutting the engine just by about 0.2 to 0.3 seconds, instead of dropping the velocity, your vehicle already has a certain momentum. So you retain that momentum and you drop to a slightly lower RPM range. So instead of dropping 2500 RPM, you might drop 2300 or even 2000 in some cases. So this is how a Quickshifter works. Now, if this is clear, let's look at what is the possible drops in RPM with each gear. Now if you are in first gear and if you upshift at 8000 rpm, you will end up dropping 2500 rpm. Now as we go higher and higher, the biggest drop will always come from first gear to second gear. This is something that is evident everywhere. That's why when you shift from first to second, you will either hear a hard thud, or in some cases it feels like a little more jerky. So that is in first gear. In second gear, the drop in rpm or the change in rpm will be around 1009. In third gear, it will be 1500. Fourth, it will be 1000, and from fifth to sixth, it will be 1100. One thing to note, how the rpm changes in upshift, the same way it changes in downshifts. Now when you're downshifting, you'll always see that your rpm tends to go up. All we have to do is, let me clear this once before I explain that part. Let's say you're in sixth gear at a speed of 140. You start braking, and the moment, let's say, you hit 5 or 6000 rpm, what do? You downshift. The moment you downshift, it tends to go to higher rpm. This is why rpm reduces when you upshift and rpm goes up when you downshift, because there is a certain road speed, and the road speed and engine speed has to match for a given gear. If this is clear, let's see what speeds are achievable in what gear. What we have here is, this is around the peak torque, the peak power range. At peak power, let's look at what is the corresponding speeds that the engine can do. Now this is the peak power range and this is the peak torque range. For the best acceleration, it is always suggested that you upshift at the peak power and ensure that you land up in peak torque area. So this way what happens is, you upshift here and you try to go here. This is the most efficient way in which you can gain speed. You can take it all the way here and ensure that you drop it very, very close to your peak torque area. Now, this is an experiment that you can try out. Do it under safe condition. Moving on, there is an interesting video that I want to show you. Let me play a video of the engine revving, and we will look at what is the signature of the engine is like. I'll explain what this video is and what it means, but for now, just go through the video once. So we'll go to a specific part of the video where the bike is just idling. Yeah, check this out. Now, remember this 114 Hertz. Now, let's take a look at different parts of this graph and what it means and what we can take away from it. Now, the first thing we have here is the frequency range. Now, what is frequency? Frequency is basically the inverse of time, or let's understand this better with an example. Let's say your engine is running at 6000 rpm. Frequency is essentially cycles per second. So how many cycles are happening in a second? Now, if I divide rpm by 60, I get revolutions per second. Revolutions is cycles, so cycles per second. So 6000 divided by 60 is around 100 revolutions per second, or 100 Hertz. Hertz is the unit for frequency. At 100 Hertz, which is 6000 rpm, your engine or your crankshaft is rotating 100 times a second, and half of that is your combustion frequency, which is your engine, your spark plug is firing 50 times a second. Now look at the engineering marvel here. You try to imagine this and you'll actually understand how beautiful IC engines are. 50 times a second is essentially 50 hertz. So your crankshaft is at 100 hertz and your combustion frequency is at 50 hertz. Now, like this, there are several things that are happening that contribute to the sound of the engine, and that is measured here. Let's say there is a 100 hertz activity that is happening. This graph will show you at 100 hertz what is the sound and sound energy that is created. So the y-axis you have here is your sound energy, that is in dB. Now if I take the sound energy and plot it over time, that is what we have here. This is like stacking a bunch of CDs, and if you look at the CDs from top, what you see is what is represented here. And if you flip the CD, if you pick one CD and see what is the reflections and what is happening there, now that is whatever is shown here. Let's understand what is happening during idling, high RPM idle and rev. The idle RPM of the KTM is anywhere between 1.5 to 1.8 thousand, 1500 to 1800 RPM. In this range, if I divide 1800 by 60, I get 30 RPM, correct? So 1500 is again 25 hertz. So 25 to 30 hertz is what you'll see. And you'll see small lines here. So these are called harmonics. What does that mean? In simple words, let's say there is a 30 hertz phenomenon. You will start seeing this repeat every 30 hertz. So 30 hertz, then 60, then 90, 120, so on and so forth. Sometimes the repetition could also change in different ways, where you might see 30, 60, 120. So there will be certain harmonics which are actually predominant. So that could be one of the reason where the primary frequency or fundamental frequency has a certain energy, then the energy drops, then it picks up again. Before we get into any of that, let me tell you what are the contributing factors to different frequency bands. Between 0 to 50 hertz or 0 to 75 hertz, you have your combustion frequency. Between 0 to 150 hertz, you have your crankshaft frequency. Some bands, 75 to 150 hertz, where you have your valve train. What is your valve train? Your intake and exhaust valves are opening and closing, right? So with every cycle, your intake opens, stays open, closes. So your intake and exhaust valves are also moving in certain frequency bands that are related to your engine RPM. Next, you have around 150 to 250 hertz. Now, this is where you see the exhaust frequency. Then you have your 250 to 500 hertz, which can be contributed by the intake sound. Now, if you've heard the Triumph Street Triple, there is a loud intake sound. There is a zzz that comes in because of the intake. There is an induction sound that is coming. Now, if you look at the Triumph engine and if we probably do a similar exercise there, we should see a peak at 250 to 500 hertz. Next, there is 500 to 800 hertz. This is contributed by your cam chain. There is a chain that is connected to the cam, which also goes to the top. Then you have your gear meshing that happens. 800 to 2000 hertz. Now this range, you will see your piston ring flutter, your valve springs, and then your injectors. Next, 2000 hertz to 5000 hertz. This is where the structure borne noises are predominant, and this is also combined with something called engine knock. Engine knock is where you hear a metal to metal sound. This happens because of improper combustion. There will be pockets of combustion that is happening that creates a lot of damage to the engine, the piston rings, the valves. So this is a separate topic in itself. We'll talk about this in some other video. And then you have your engine block, which can also have a resonant frequency in this range. Then you have your frame that can amplify certain frequencies, so on and so forth. And anything above 5000 hertz is generally your airborne or aerodynamic noise. You can also have your pump and other components that contribute to this. This can also have some bits contributed from the chain. If I start dividing this axis into different segments, these are the contributing parts. Now let's look at the high RPM idle. In high RPM idle, we have peaks here, which means on the 390, the contribution, the primary contribution is between here and here. Now, this is one primary contributor for what sound you hear, and this is the second contributor. The line is slightly off. So let's look at what are the things that are contributing to the sound of the engine here. So 0 to we have about 150 hertz here. So 150 hertz, you have your combustion frequency, your crank, and your valve train. Now that is contributing to one majority of the sound, and there is certain high frequency sounds that are coming in. Now this is between 1000 to around 3000 RPM, if I'm not wrong. 5000 RPM maybe. So contribution from the valve springs, injectors, knock I don't think is there. It's a rare phenomenon and will only happen under certain conditions. So predominantly I would say in low RPMs you have your combustion frequency, your crankshaft frequency, and your valve trains. And at higher RPM frequencies are contributed mainly by the valve springs, the injectors, and probably some amount of piston flutter. This may or may not be happening, but these two could be the contributing factors. Now, if that is clear, let's quickly identify what is happening. Major frequencies here, similar sounds. Here, the sound band in idle condition is limited quite a lot. Again, from 1000 to probably 2000 RPM. Similar bands here. But when I rev the engine, you see this? There are harmonics that are triggered, which means the moment I rev the engine, you see these small peaks. It's like your echo. When you're standing on top of a mountain and you scream, the first scream is long, and then you see the echoes. The time between the echoes will actually keep dropping. That is exactly what is happening here. Now, when you rev the engine, you see the energy bands that are here. Very high, right? So it goes all the way from 10 hertz or 20 hertz to up to 500 hertz. And in the higher frequency range also, the energies are higher from anywhere between 800 hertz to around 5000 hertz. Now this means there is good contribution from the engine and there is good contribution from the structural components as well. Now if this is clear, you can try out what is happening, try out and see what is happening on your own engine, where you download this app and then you measure different aspects of your engine and try and see if something is normal or if something is off. Now, there are two more interesting things that we'll have to speak about. And with that, we will end this video. One is something that is new to motorcycles in this price range or in this category, which is you see two O2 sensors. O2 sensors are essentially required to measure how well your combustion is happening. Now, on most vehicles, you will see one of this. Now, what is the job of the sensor? So, a clean combustion will always happen here, let's say. Now, if there is more fuel being pumped into your engine will start running rich. This is when you see your black smoke and things like that. This is an exaggerated view. And when your air is higher and fuel is lower, that is when your engine is said to be running lean. These sensors over here, the only job that these sensors have is to measure whether your engine is running rich or running lean. Now, to control emissions, in some cases, let's say when your engine is running rich, the engine will start spraying less fuel so that the engine comes back to the ideal state of running. Now, if let's say your engine is running very lean, your ECU will actually tell the engine to start pumping in a little more fuel so that a lean mixture comes back to your perfect stage of combustion. While most two-wheelers run very well with a single O2 sensor, you will see that the KTM 390 have two O2 sensors. What does this mean? So if you look at this bulge, now this is a catalytic converter. Now the role of a catalytic converter is to ensure that you have cleaner exhaust emissions. Now there are certain chemical reactions that happen if your engine is running too rich, which might result in hydrocarbons being put out from the combustion. In this case, the catalytic converter is responsible for oxidation of this. So when oxidation happens, your hydrocarbons are converted into carbon dioxide. In cases where your engine is running very lean, then there are already oxides of either nitrogen or sulfur that are there. Now in this case, reduction happens. KTM 390 has one pre-cat and one post-cat. So there is one sensor before catalytic converter that we call it pre-cat. There is one after the catalytic converter which we call as post-cat. Now this is not new in terms of cars. Cars are generally known to use this tech. Why do they do it? Now if you look at the signal trace of the pre-cat, it is a very noisy signal. It is varying too much, and with this, the kind of control you have, the kind of control the VCU has in controlling the combustion is slightly erratic. Now if you look at post-cat, if you look at the same time trace at the same point in time, you'll see that the variations are actually slower than what you think. By considering both these inputs, your engine control unit ECU is able to better control combustion, which leads to better control in emissions and in some cases higher efficiencies. So that is why there are two O2 sensors on the KTM Adventure and the KTM Duke. Now beyond this point, we will have to diverge and separately study the Adventure 390 and the Duke 390. If you are interested in this video, let me know in the comment section. We will make an extension of this and we will continue from here on. Until then, ride safe and Godspeed.